Hello everyone. I apologize, this is going to be a little bit of a longer video, but this is a new video for this year for our coronavirus time. And it's one that we usually spend quite a bit of time on in class. So I'm going to do the best I can to get through this in a reasonable video time. But it might get a little bit longer than most videos, but this is a really important one. So we're going to start talking about graphing today. And as I put in the email, if you need some graph paper when we get to actual graphing in our next section, you are welcome to swing by the school. I've printed and placed a bunch of graph paper in the front entryway of the school. You can come by and grab some if you need to for your own printing purposes. All right, so we're going to look at our rational function, and just like we've done with all of our other shaped graphs, we're going to start off with the parent function, or as we like to call it, the mother function. And the mother function for a rational is y equals 1 over x. Because if you remember what it means to be rational means to be in a fractional setting. So this is our simplest possible fraction. And in order to be a rational expression, you need to have a variable in the bottom. And so therefore 1 over x is our simplest form of a rational function. And so we're going to check and see how this parent function behaves, how the mother function acts, and what it looks like. Now, having said that, I'm just going to let you know now, and you're going to hear this a few times, rational functions aren't like parabolas. They aren't like absolute values. They don't all look the same. They all look a little bit different. And we'll get into why as we go deeper into this. And so the parent function is going to introduce some ideas, but it's not going to be like a parabola where every graph is going to look like this. But there are components that all the graphs will share. So just like we do with every other function, if we don't know what a graph's going to look like, we go ahead and plug in points. So if we plug -2 in for x, that gives us 1 over -2. Well, 1 over -2 would be -1/2. All right, so that's 1 point on our graph, -2 comma -1/2. If you plug in -1, 1 over -1 is -1. Then we get to 0. 0 is a problem. We're just going to leave that alone for a little bit. We'll come back to that. We'll plug in 1 for x. 1 over 1 is 1. 1 over 2 is 1/2. Now, a clear pattern isn't really showing up here. We have -2 comma -1/2, -1, -1, 1, 1, 2, 1/2. We really don't have a pattern showing up here. So let's think a little bit. Before we get to the 0, let's just think a little bit. If you plug in a bigger number like 10, if you plug 10 in for x, you're going to get 1 over 10. So 1/10. You're going to get this really small value. Sorry, that missed a little bit on my graph, but you get the idea. You get 10 comma 1/10, this extremely small number. So what we can figure out here then is, if you plug in a number like 100, 1/100th is going to be a really, really, really small number. So what's happening here is, I usually explain rational functions in the idea of an annoying little brother. And if you had an annoying little brother, I'm sure at some point you and your brother interacted in the I'm not touching you game, where you get as close as you can to them without actually touching them. And it's about the most annoying behavior you can have. And that is what is happening with the rational function here. And I'm having trouble drawing it because I'm a little limited here. But this x value as x keeps getting bigger, y keeps getting closer and closer to 0, but it'll never actually touch it. So you're getting as close as you can possibly to the axis, but you'll never actually touch it. So that's what happens as numbers get bigger. And the same thing will happen in the negatives. As you continue to plug in negative numbers, we'll get closer and closer and closer to that x-axis without actually touching it. Now, let's look at what happens as we get closer to 0, because we said when x is 0, we have a problem. So as we get closer to 0, we think of a number like 1/2. If you plug in 1/2, you have 1 over 1/2. Well, when you divide by a fraction, you copy dot flop. 1 divided by 1/2 is 1 times 2 over 1, which is 1 times 2, which is 2. So if you plug in 1/2, you get 2. Sorry, that wasn't very good there either. If you plug in 1/10, you'll get 10. If you plug in 1/100th, you'll get 100. So what happens is, as the fractions get really, really small, like 1/100th for x, your y value gets really, really big. So your graph looks kind of like this, where we approach the x-axis as we leave, we approach the x-axis as we leave, and then vertically we approach the y-axis and we approach the y-axis. So this is the shape of the parent function for a rational. So let's talk quickly about this 0 idea. If I plug 0 in for x, I get 1 over 0. And as there's signs in my classroom and stuff all over that we've talked about this, you can never, ever divide by 0. 1 divided by 0 is actually an undefined value. And when you look at it on the graph, we said we approach the y-axis, but we never actually touch it. That point is undefined. How you graph an undefined value on an actual grid is with this brand new word that we're going to define in a second that we call an asymptote. An asymptote represents a vertical line that you will never ever touch. So let's go ahead and talk about asymptotes. So let's take a minute and talk about asymptotes. Asymptotes, we just showed, they're used to mark an undefined value on a graph. All right, well, the question comes up, what makes a function undefined? Well, a function is undefined when the bottom of a fraction is equal to 0, and that goes back to our rule that you can never ever divide by 0. So an asymptote is used to mark an undefined value on a graph. It's undefined because the bottom is equal to 0. Therefore, vertical asymptotes occur when a function is undefined, meaning the bottom is equal to 0. So that's what we're going to focus on today, is finding asymptotes of graphs. All right, let's get to what our homework's going to look like today. Today you're going to be asked to identify the x values for which you will have the asymptotes of a function and the zeros of a function. So we're going to start with a very simple example. A simple rational function, f of x equals x minus 3 over x plus 5. So we're going to find where the vertical asymptote should occur. To do that, we're simply going to say VA, to abbreviate vertical asymptote. There's going to be a vertical asymptote when x is equal to some number. All right, that vertical asymptote is going to occur when x is equal to the number that makes the function undefined. Asymptotes represent undefined values on a graph. So therefore, the undefined value will occur whenever the bottom is equal to 0. So we simply look at the bottom and say, what would make the bottom equal to 0? -5, because -5 plus 5 is equal to 0. Now, hopefully, there's something going off in your brain saying, we've already done this, we've already done this. These are excluded values. What you did when you found the excluded values is you found where the function didn't exist, where it was undefined. That's where a vertical asymptote occurs on the graph. So you simply look at the bottom and say, what would make that be 0? That's where your vertical asymptote will lie. Now you're also asked to find the zeros of the function. So what will make this function equal to 0? Well, this goes back to fraction rules again. if you want to make a fraction equal to 0, you need to make the top be 0. Because we know if the bottom is 0, the function is undefined. But if the top is 0, then you would have 0 divided by anything. 0 divided by anything is 0. So the zeros of this function are going to be at x equals 3. So for today, we're not actually going to draw in any graphs. We're not going to even need graph paper. We're simply going to identify critical values on the graph. The critical values for this one are going to be that it has a vertical asymptote at -5, and it's going to go through the x-axis at x equals 3. That's the 0 of the function. All right, we're going to look at one more example, and then I'll stop this really long video. All right, so in this example, we're going to have a little bit of a higher level question. And it's asking us to find all zeros and vertical asymptotes of the given function. And our function is y equals x squared plus 7x plus 10 divided by x to the third minus 5x squared. Well, in order to do this, we're going to go back to what we've done in everything for this entire chapter. Everything starts by looking at the function in its factored form. So let's go ahead and put this into factored form. On top, we're looking for numbers that add to 7 and multiply to 10. If we do our diamond problem, we get 2 and 5 for those factors. On bottom, I recognize a GCF situation. Both equations have at least 2 x's in them. So I can factor out an x squared from both, leaving just an x here. And when I divide x squared out of this, I'm left with just 5, x minus 5. So this is our factored form of our equation. Exactly the same thing you've been doing for everything else. Once you factor, we can identify where the zeros of the function are going to be and where the vertical asymptotes are going to be. So the zeros are going to occur whenever the top of the fraction will be 0. So your zeros are going to be at x equals -2 and x equals -5. Those are the two places where this graph will cross the x-axis. They will have x-intercepts or zeros at x equals -2 and x equals -5. The vertical asymptotes occur when we make the bottom be 0. So we look at the factors of the bottom. We have 2 factors. The first factor would be 0 if x is 0, because 0 squared is 0. And the second factor would be 0 if x equals 5. So in our next section, we're actually going to start putting this information on a graph. But for today, we're just going to be identifying these critical values on a graph. Where do vertical asymptotes occur? And where do the zeros occur? All right, good luck. Zoom in if you need me.